In this video I will show you how to do linear regression both in the statistical way and then in the machine learning way in Python. So for that we'll be using Prython 2.0. You can download Prython from www.prython.com. It is available only for Windows. And you can download my project from the following GitHub repo over here. It's linear_regression.prython. So the idea in Python is that I can put my code into panels like this and I can connect them on random. In this simple example, I will be using the diabetes dataset. It's a very well-known dataset from scikit-learn that I am importing here. And I am just loading the X and Y. I will only have one variable, and that will be it. In order to run everything, I just run below, and then that's fine. You can see here Python loads all the NumPy arrays. So as you can see here, I have diabetes X and diabetes Y. If I go below, not only I have diabetes X and Y, which were defined here on top, but then I have Y and X that were defined here. And the same happens for this panel over here. But let me explain what's going on. So what I did was to connect two different experiments or two different panels containing two different approaches. One is the statistical way of doing linear regression, and the other one is machine learning way. The mathematics are exactly the same, but the way we interact with the model and the way we use the outputs of the model is really different. So in the machine learning way, the idea is to use the model for prediction. So we only care about how well the model predicts. That means that we usually separate the data into a training and test dataset. We train it on the train dataset, and we use the test dataset just to validate the model, just to see how it works, which is exactly what I'm doing here. You can see where we're printing the mean square error, for example, the R square score. This is done on the test dataset, but the model was fitted, if you look closely here, .fit on the train dataset. And then we're just plotting here, and probably this is not very important, but we're plotting, and this is what we're doing. So we have X would be the independent variable that we're using, Y is the target. We have this cloud of points, and we just want a line that goes through the middle. So that's the idea of linear regression. And that's really it. We don't do any kind of analysis. We maybe print a few things, but that's really it in the machine learning world. Whenever we need to use the model, we just call .predict, and that's really it. That brings me to a statistical way. The statistical way is kind of harder. It's kind of an art and requires a lot of practice to master. The idea of the statistical way is to use a model to understand the relationship between variables, not to predict. It can be used for predictions, but it's not the main goal. It's not really why we build models this way. So what we do here, we'll use in this case we use the library, the stats models library. There are other libraries, but this is the most famous one for statistics. For the machine learning way, if you look closely, I use scikit-learn, which is the standard machine learning library for Python anyway. So we just call OLS. OLS stands for ordinary least squares. So it's the same way same thing we use here in scikit. But the difference is that the output gets printed in a different way, and we can see different things. So let's see that. Here model.fit is used to fit the model, and then we're just printing the summary. So what we can see here are different things. So first thing is that we can see the coefficients, that they're not printed automatically in scikit-learn unless we try to print them on purpose, but if not, they're not printed. The standard error for the coefficient is printed there. It's not there in scikit-learn. Also the t values, so these are t statistics, and then the p values that are derived from them appear here. So the 0 means that both of them are statistically significant, meaning that they are statistically different from 0. They're big, basically, or big relative to the variability. So this is the first thing that we usually look. Then we usually look at the R square. The R square is a number between 0 and 100, so it can be interpreted in a percentage way. So if it's close to 0, it means that the model doesn't predict anything. If it's big, it means that the model works well. More formally, we can think of this 34% as the proportion of the variability in the target that we predict with our model. So with this model, with this constant or intercept plus x1, we predict 34% of the variability, 34% of the movement in the variable, which is non-negligible, but could be better. For long and complicated reasons, we might want to use the adjusted R square if we have lots of variables, because what happens is that the more variables that we add to a model, the more the R square increases. So it's kind of difficult to compare the R square between two models, because one, let's just say one has one more variable, the R square will be bigger, but does it really make the model better? That's why we need the adjusted R square. The other thing we usually look is the F statistic. So this is a joint testing the null hypothesis that all the coefficients here are equal to 0, which is not my case. You see the p-value here is very small, so it means we reject that null hypothesis, which is consistent with what I'm seeing here. So both p-values are almost 0. We don't look at the log likelihood, and we usually look at the AIC and BIC. So this is the Akaike information criterion, the Bayesian information criterion. These are used to compare among different models. So what happens is that maybe we have 10 variables, and we do a test with 10 variables, and we do another one with 7, another one with 3. We might want to decide which is the best model, and we usually use this. We typically don't look at the degrees of freedom for the residuals or the models. We don't care about that. We do care about this. So these are the Harkivera test and Derwin-Watson test. So Harkivera test the null hypothesis that the residuals are normal or Gaussian. So that's one of the assumptions that we need in order to make inference on these statistics. You see the t-values there. They are dependent on this test being non-significative. So what we want here is to not reject the Harkivera. If we reject it, like we're doing here, because this is smaller than 0.05, it means that the residuals are non-Gaussian, non-normal, and it means that these t-tests are wrong. Here, obviously, you could argue, well, we could work not with a 5% significance rate, but we could use 2.5%, which in that case, we could almost even say that the residuals are significant. But yeah, it really depends on the significance value. Typically we use that 0.05 as a threshold, and that's why I said initially that we would reject the Harkivera, which would bring a lot of problems, because that means we need to try to fix that, probably by adding more variables or changing the model or applying logarithms to the variables, but that sometimes doesn't work. And the Derwin-Watson we don't need it because we don't have temporal data. So Derwin-Watson tests if the residuals are correlated, but that's not a problem that I would have here. And what's the main thing? So we as I said, we don't use it for prediction, we use it for inference. So what we would typically do is look at this coefficient and say, well, if I change my x1 variable in 1 unit, by how much the target y changes. So this is telling me 949. So that's typically the way we use it. If you had more variables, then we'll be doing more things. The other thing I wanted to point out is that the way I train this, I use just the whole dataset. I didn't split into training and test, which is a typical thing in statistics. We just load everything and that's it. That's really it.